Hello guys and welcome to this new YouTube channel. DSP Corner. Very creative name, Digital Signal Processing Corner. I didn't find a better one. As the name is already indicating, I'm going to show videos about digital signal processing, but especially for beginners. So very entry-level based videos. From time to time I will also make some videos where I go deeper into the details, deeper into, let's say, the algorithms and the math behind them. But for the beginning I will start with very entry-level videos. And so this is a new world for me, making videos, tutorials, or how-tos, call it however you want. And so don't blame me. I have absolutely no professional hardware here. I have no scripts where I prepared all that stuff. I'm doing it just for fun. And so also the topic for today, I chose it because I thought, oh, maybe this is an interesting or very important point in signal processing. How to plot a FFT. How to plot a fast Fourier transform result in GNU Octave. So just for the background, I'm using for the programming GNU Octave, which is similar to MATLAB, but you can use whatever programming language you prefer. I personally prefer Python for signal processing implementations because I think it's much more powerful, but for beginners I think it's easy to follow my code using Octave or MATLAB. And yeah, so the topic of today, FFT, fast Fourier transform. What is it? Still entry level, so only in a few words. A fast Fourier transform is a very efficient implementation of the so-called Discrete Fourier Transform, which is one of the, let's say, most important tools in digital signal processing. And what is it doing? Transforming, yeah, but what? So with a time domain signal, let's say your raw audio file, your audio data, and you apply the discrete Fourier transform or the FFT to it, and the output is a frequency domain signal. So we are going from time domain to frequency domain. This is what the FFT or the discrete Fourier transform is doing. But why are we doing it? Because the frequency domain signal shows us which frequency components build up our time domain signal. In the time domain signal we see what's going on with the signal over time. In the frequency domain signal we see what's going on with the signal over frequency. And yeah, and I think to apply a FFT to a signal is a very, very important task in signal processing, and that's why I chose this topic here. So let's directly jump over to Octave and play around with it. So as most of the MATLAB or Octave scripts, I start here with these three important lines: clear all, close all, CLC. I forgot the A, it's quite late. So these three lines mean clear all, clearing all workspace variables, which will be shown here. Close all means closing all maybe opened windows, and CLC is to clean the command window. So I think this is, you will find these three lines in most of the main scripts of MATLAB or Octave programs. So we are in the field of digital signal processing, meaning we have a digitized signal, and related to every digitized signal is a sampling frequency. So let's define an arbitrary chosen sampling frequency, 10 megahertz or 10 megasamples. It's called FS, sampling frequency. So yeah, FFT applied to a time domain signal. We need a time domain signal. We could use a continuous wave signal like sine or cosine, but let's choose a more advanced signal like a chirp signal. A chirp signal, you will find it everywhere in digital communication, radar, signal processing, or elsewhere in the field of digital signal processing. A chirp signal is a signal that is chirping. This means it starts at a frequency, starting frequency, let's say 1 megahertz. And then the chirp is linearly increasing its frequency over time until it reaches a stop frequency, let's say 2 megahertz. So we start at 1 megahertz and linearly increase our frequency until we reach 2 megahertz. So 1.1 megahertz, 1.2 megahertz, and so on until we reach 2 megahertz. And for this linear increase, we need a certain time, which is called chirp duration. I call it T-dur. And let's say we give our chirp 100 microseconds to increase the frequency from start to stop linearly. So start frequency, let's choose an arbitrary frequency, let's say 500 kilohertz, and a stop frequency, let's say 1500 kilohertz. Yeah, let's align these bodies here that it looks more professional. And so these are the basic parameters that define our chirp signal. So we start at 500 kilohertz and then we linearly increase our frequency until we reach 1500 kilohertz over a time of 100 microseconds. By the way, we already know our signal length in samples because we have defined our sampling frequency and we have our overall signal duration, 100 microseconds, and the overall signal length in samples is then sampling frequency times the duration of the signal, should be 1000. Octave proves me right, it's 1000 samples, signal length in samples, not in time. In time it's 100 microseconds. So okay, to create our signal we need a time domain vector beginning at 0. The increment between the time domain samples of our digitized signals is the inverse of the sampling frequency. So the time domain signals are 1 divided by sampling frequency apart from each other until we reach our overall signal length in time, T duration. And I'm doing something strange here. I'm subtracting 1 minus divided by sampling frequency. Why I'm doing it? Because it's common to count from 0 to n minus 1 or from 1 to n, because we start here at 0 and go up to n minus 1. This is why I'm subtracting this minus 1 divided by sampling frequency. This is our time domain vector T-back. Now we have to create a chirp. I call our chirp x real. Why I'm calling it x real? So x is common for defining a signal and real means real value signal. Why real valued? Because this signal that I will create in a second has no imaginary part. After we created the real valued version, I will also create the complex version to see the difference. So let's create our real valued chirp signal with a sine wave. We could also use a cosine wave, but I prefer the sine wave because if we start at time 0, the sine of 0 is 0. So yeah, I like it to start at 0. We could also use the cosine, then we would start at 1. Depends on you guys. So let's write the chirp formula. It's 2 times pi times start frequency times t vector. I will stop here, it's not a chirp, but this here is a normal continuous wave, a sine wave with the frequency of f start 500 kilohertz. And now the linear frequency modulation comes into the game. We are linearly increasing our frequency over a certain bandwidth, and the bandwidth is the stop frequency minus the start frequency. In this case 1 megahertz, and divided by 2 times the time that we need to go from start to stop, times T-WAC to the power of 2. Why this formula looks like it looks, I will explain in another video. For the beginning, deal with it. This is the chirp formula, if I made no error. And let's plot it to see if it's really a chirp. So we create a graphic, a figure. We plot our time domain vector T-WAC against our signal vector x real, the real value chirp version. Because we want to look professional, we give the axis names. So the x-axis is called time, because it's the time domain vector that we plot there in seconds, and the y-axis is indicating us the amplitude, let's say in volts. It's volt, it's okay. And then we also turn on the grid because I think it looks nice. So, and fire up this body, see if we made any errors. Okay, I have to show you the plot window, but I already see that we made it right. So where is it? So guys, here we have our chirp signal. As you can see, our x-axis is giving us the time starting from 0 to 100 microseconds, which is, oh, I have to place my face in another corner. So time from 0 to 100 microseconds, like we defined it. This is our chirp duration, the time that we need to go from the start frequency to the stop frequency. And we already can see that we linearly increase the frequency over time, because here the samples are more narrow than here. And on the y-axis we have the amplitude from 1 to -1. Okay, the chirp looks good. Yeah, it looks good. Okay, let's go back to our workspace. And now we're coming to the interesting part. We now apply the FFT to this time domain signal. And it's quite easy. Let's define a variable for the FFT output for the frequency domain signal. Let's call it x real, and x with capital letter. And then it's just FFT times x real. FFT x real. But for the time domain vector, we have generated, for the time domain signal, we have generated a time domain vector T-WAC. For our frequency signal, we also define a frequency domain vector. Let's call it F-WAC. So F-WAC is the frequency domain vector. Because we're in the digital domain, this frequency domain vector goes from minus the half of the sampling frequency up to plus half of the sampling frequency. Here from minus 5 megahertz, because our sampling frequency is 10 megahertz. So we go from minus 5 megahertz up to 5 megahertz, because it's Nyquist. And yeah, another important parameter if we talk about the frequency domain, the length of the frequency domain signal. We already saw that our time domain signal has 1000 samples. Sampling frequency times the duration of the signal. In the frequency we also have to define the length of the signal. I call it NFFT. And here I want the time domain signal and the frequency domain signal to have equal length. So that's why I just say, okay, the length of our frequency domain signal is the same as the length of our time domain signal. This is our NFFT. And now we can build up our frequency domain vector. We know our frequency domain vector has the length of NFFT. We know that our frequency domain vector will go from minus 5 megahertz, half of the sampling frequency, up to plus 5 megahertz, half of the sampling frequency. So it's minus NFFT half up to NFFT half minus 1. This minus 1 here because we are going from a minus the half of NFT to 0, and then we have the 0 in the positive part and we have to subtract it to get to be still even. Times Fs divided by NFFT. So let's see if it's right. Let's have a look at FREC. Yeah. FREC, where is it? It starts at minus 5 megahertz and goes up to 5 megahertz. Okay, so now we have the frequency domain signal length NFFT. We have the frequency domain vector FREC, and now we need the frequency domain signal. And the frequency domain signal, we get it when we apply our FFT to our time domain signal. So it's FFT from X real, and then the FFT function, you can tell it how long the output should be, and we wanted to have NFFT samples, so we pass also NFFT as argument to the function. That's it. Let's fire this body up. Now in X real, or now X real is our frequency domain signal. That's the whole magic. We now have generated a frequency domain signal, but now we want to plot it. So again, let's create a plot. This time we are plotting the frequency domain vector FREC against our frequency domain signal. But wait, our frequency domain signal is complex because the FFT generates complex outputs. So we have to use the absolute value to plot it. And I will show you something and then explain it. Let's fire this guy up. Oh no, to be professional, we are adding the labels. Frequency in hertz is our x-axis, our y-axis is amplitude. So, and again, returning on the grid. So let's fire it up. And I'm going to show you the window. Wait. Yeah, here it is. And wait. So this is the output, or this is the FFT, but wait a minute, there's something wrong. So as you can see, the signal here starts at, I don't know, 3.5 and goes up to 4.5. This is not what we created. We created a signal that should start at 5 and goes up to at 500 kilohertz and goes up to 1500 kilohertz. Yeah, because we made one mistake. If we go back to our Octave workspace, our failure is here. If we, let's say, here, the output of the FFT is X real, but Octave and MATLAB implement the FFT and also the other programming languages in a way that the output, the frequency domain signal, is ordered in the following sequence. First we have the positive frequencies, and then we have the negative frequencies. But for our plot we want to have on the left side our negative frequencies and on the right side our positive frequencies. and in the middle our DC component. So we have to tell Octave, hey, please order the samples, the frequency domain samples, in the right way to plot it, and this is done by FFT shift. FFT shift takes the vector x real, which is ordered in a way positive frequencies, negative frequencies, and takes the negative frequencies part and puts it on the other side. Because then, if we now fire it up again and have a look at our output, here it is. Now we have the right plot. So what can we see here? We have a signal from 500 kilohertz going up to 1500 kilohertz. Yeah, it works. And we now can also see why I called it X real, real valued, because our frequency spectrum is symmetrical. We have our chirp here and also on this side. Here zero, so positive frequencies and negative frequencies. This is how a real valued signal behaves in the frequency domain. Now or later I will implement the chirp in a complex version, and then we will see that we only have one of these spectra, positive or negative. So, but having a closer look at the FFT here, so we have our frequency domain vector or frequency domain axis here, which goes from a bit longer. The actual plot is a bit longer than we defined it. It goes from half the sampling frequency, -5 megahertz, up to 5 megahertz. Octave is enlarging the plot up to 6. So, but it's actually only a signal from -5 to +5 megahertz. So half the sampling rate up to -half the sampling rate up to half the sampling rate, Nyquist. And in between we have our chirp, which increases its frequency linearly from 500 kilohertz up to 1500 kilohertz, 1 megahertz of bandwidth. And why we have this phenomena here that it's not equal, and why we have this problem here that we do not hit exactly 500 kilohertz, I will explain in the next video. But what we see here is the FFT plot of our real valued signal. And what we also can do, we plotted the absolute value, and it's a nice representation if we plot it also in decibels. We will do this now because it's easy. So let me choose the right window to show you. So here we are back again in our workspace. So here we plotted the absolute value of X real, which again is a complex signal, the output of the FFT. And to plot it in decibel, it's 20 times logarithm of 10, base 10. That's why you have to add 10. And plot it again. And then we can add here amplitude in decibel. And so here we now have our FFT plot in decibels. Looks a bit nicer, especially if you have several signals and you have a high dynamic range. Then the decibel representation is better to visualize what is going on in the frequency domain. Okay, again we have our two-sided spectra here, positive frequencies, negative frequencies, and now we generate a complex signal, and then one of these spectra here will vanish because a complex signal has another symmetrical spectrum, and now we will create it. So okay, this switching between the windows that I have to show you is very annoying. Maybe I will find a good capturing software. Okay, so again, we now create X complex. We have to go back to time domain because we have now to create a complex time domain signal, which for the chirp is 1 times imaginary, J, Y, call it however you want, times, and then it's the same formula as we have here. Exactly the same formula, we only add this 1 times J and replace the sign with the exponential function. That's it. That's the whole magic. Now we've created a complex chirp. Again, let's plot this complex chirp to see that it's the same. We can use the same code, but we plot here now X complex. But wait, we cannot, or we don't want to plot complex values in a manner of plotting imaginary against real valued part. No, we choose the real value part of the complex signal and plot it. So, to show you the window, again, here's our chirp. It's the same as before, but you see something, it's not exactly the same. Why? Maybe you guys already guess it. We start here at 1 and not at 0 as we did it with our originally generated chirp. That's because for plotting the complex value signal we chose the real part. And remember, exponential function e to the power of j something else is the same like the cosine of this j to the power of something plus j times sine. So the real value part of the complex signal is the cosine, the complex valued part of the complex signal is the sine. So to get the same time domain plot as we got with our sine wave, we have to plot the complex part, which is quite easy. We just change here real against IMEC, imaginary, plot it again. Here it is. Let me show it to you. That Octave is proving me right. So, and now we start at 0, like we did with our real valued chirp that we generated with the sine wave. So, but actually it doesn't matter, it's just to give you a feeling about it. So, okay, now we also want to plot the FFT of this signal. Again, we create first the length of our frequency domain signal. Again, we choose the same length as our time domain signal, X complex and FFT. Then for the time domain signal we needed a time domain vector and we need again a frequency domain vector. I repeat it, we do not need to repeat it because we already have defined the FREC here. So yeah, no need to repeat it, but again we have our F vector with our length and FFT, which is the same length of as the time domain signal, and because the complex signal and the real signal have the same length, we can leave it that way. We can also leave our frequency domain vector the same, and we only have to create our frequency domain signal, X complex, X capital letter, and it's again FFT. Then we pass our time domain signal to the function X complex, and the length that we wish Octave to produce the FFT and FFT. That's it. Now we've created the FFT of the complex signal. So now let's plot this body. Oh, it's the wrong. We take this one. We start plotting it with in decibels. So 20 times the logarithm of our X complex signal. Absolute value, because X complex is a complex signal. The FFT output is always a complex signal, and that's why we take the absolute value and we plot it in decibel, 20 times the logarithm of the base 10, because it's convenient to plot it, especially if we have a high dynamic range in our signal spectrum. And now let's fire this body up. Window number 4. Okay, then I have to show you window number 4. Here it is. Yeah, and as promised, we now have only only a single-sided spectrum. Only this body here, and again from the frequencies, I hope they are right. They are not right. Why are they not right, guys? You already know it. Because what is FFT doing? Producing the output in a way, positive frequencies and then the negative frequencies, and we have to flip it. The negative frequencies are on the left side. This means that we have again to add the FFT shift function. Now it's aligned in the right way. Let's fire it up again. See if the frequencies are consistent with what we would expect. So 500 kilohertz up to 1500 kilohertz, and as we can see, yeah, it's right. We are here from 500 kilohertz up to 1500 kilohertz, linear frequency increase over a bandwidth of 1 megahertz, starting from half of the sampling frequency minus 5 megahertz up to 5 megahertz. So that's the whole magic. But what if we want to get this body here on the left side? No problem, I can show it. So easy. That's why I love signal processing. The only thing that we have to change in the complex signal is, here is the complex signal, only at a minus sign, because the exponential here, minus, will mean, okay, we now have the frequencies on the negative axis. Plot it again, see if I'm right. Switching between the windows is very annoying. Here it is. I was not lying. Now it's on the left side. From minus 5 to minus 15. 100 kilos. Great. That's easy. If you remember the first plot that we made from the complex signal, the frequency components have also been aligned to the left. This was because of aliasing, because we FFT shift was not applied to the signal, so positive and negative frequencies have been changed, not in the right order, causing aliasing. This was why we had the components on the left side. So, but now everything is right. So let's go back to our workspace. Okay, so now we know how to plot. First, now we know the important 3 parameters of a chirp. The duration of the chirp that he needs to linearly increase a signal's frequency from a start frequency to a stop frequency. We know how to generate the chirp in time domain. As a real valued signal, it's this formula here, x real. As a complex value signal, it's this formula here. The same, but we replaced the sine function with the exponential function and added the imaginary sine j. So these are the time domain signals. So to these signals we have applied the FFT. And again, FFT is producing a frequency domain signal. So for the time domain signal we need a time domain vector here. So we also need for the frequency domain signal a frequency domain vector. For the time domain signal we have an overall signal length, which is sampling frequency times chirp duration, 1000 samples. So also for the frequency domain we have to define the length, which is nFFT, and we said okay, we want to have the same length in time and frequency domain. So then we have created our FFT output for the real valued signal by just applying FFT to our time domain signal and tell the FFT function, hey buddy, the output should be an FFT, which is the same as in the time domain signal. And then the FFT function output is generating X real, but in a way that positive frequencies and then the negative frequencies, and we have applied FFT shift to this output to align it in a way that we need to plot it negative frequencies, DC component, positive frequencies. So then we did the same for the complex signal. FFT of the complex signal, FFT length, and we have applied FFT shift again to it. For plotting our FFT signal, it's important we plot our F vector against our FFT output, but because the FFT output is complex, we plot absolute values. And because it's nicer if we have a high dynamic range in our spectra, we also plot it in decibels, 20 times the logarithm of 10. That's it. That's the whole matching of plotting FFT of real valued and complex valued signals. So one last thing about FFT, which is a nice application of a FFT I want to show you, is the spectrogram. Octave and also MATLAB and all the other fancy IDEs or programming languages have packages that you can install, and one of the packages I'm loading now is the signal package. Why I'm loading it? Because there's a function, I will write it here, pk package load signal. So we load the signal package, it's a toolbox, an add-on, and this signal package is giving us a function called spectrogram. And what is spectrum? Spectrum stands for spectrogram. Spectrogram is an image. The output is an image. You can have a look, oh, what is going on in the frequency domain over time, because our chirp is linearly increasing the frequency over time. In our spectrum, if I go back to our FFT output, you only see, okay, yeah, I see there's something going on from 500 kilohertz to 1500 or minus, and but you don't see at what time it happened. And I told you, oh, it's doing it linearly over time from start to stop over the duration of 100 microseconds. So we need a representation to see that it's actually linearly increasing. And this is where the spectrogram comes in. The spectrogram is nothing else than in a basic version. There's also additional features like windowing and overlapping and blah blah blah. But to demonstrate how we can use the FFT for it, I'm using the spectrogram in a way that it's an image. Image has rows and columns, that every column of the spectrogram of the image is a FFT of a certain length of our time domain signal. Instead of, what does it mean? Yeah, it's confusing. We have applied our FFT to our whole signal. Let me show it to you. I have to show you the workspace again. We have applied the FFT to our whole signal here, for example. We took the whole signal and applied the FFT to it. What if we only take pieces of the signal, apply an FFT to it, then take the next pieces, apply an FFT to it, next piece, apply an FFT to it, until we reach the end of the signal, and then we align this several FFTs as columns of an image. This is the spectrogram. And then we can see what is going on in frequency over time. And this spectrogram function is inside the signal package that you can install in Octave or in MATLAB. And so let's do it. X real, we could also use X complex. So instead of using NFFT, which is 1000 the length, we take only 128 samples of the signal, apply FFT to it, next 128, and so on and so forth, and pass the sampling frequency to it. Again, figure, and then we plot it. Oh yeah, this looks nice. I have to show you the output. Where is it? Figure number 5. So here it is. This is the spectrogram. The spectrogram of our chirp signal. What can we see here? Again, time domain. We are going from 0 to our 100 microseconds, and here we see the frequency from 0 to half sampling frequency 5 megahertz. And we see here a linear increase in frequency over time. We start at 500 kilohertz and linearly increase the frequency up to 1500 kilohertz over the chirp duration of 100 microseconds. And each of these columns here, I chose a rough resolution that you can see each of these columns. They are indicated here. Each of these columns is the output of an FFT of the length of 128, the length that we chose to plot the spectrogram. So the spectrogram takes 128 samples of our signal. FFT is calculated, and the result is stored as a column here in this image. Then the next 128 samples are taken, FFT is calculated, and the result is plotted or stored also as the next column, and so on. And then we end up with this nice image indicating us what is going on in frequency and time, because the FFT is only showing us the frequency components, but we don't have any time information. In the time domain we only have time information but no frequency information. But with the spectrogram we have both time and frequency information. And yeah, that's it. I think this is more than enough information for the first video. Please forgive me any errors. I will upload the script and attach it to the video description, that you can download it and play around with it. But if you want to use this one, use Octave and install the signal processing package. This one here, it's package install -forge signal. Install. In this way you can install the package after you've installed Octave, or you can also download the package directly from the Octave homepage, and then navigate to the folder where your download is located and type package install signal, and I don't know what the ending is, tar, something like this. So you have first to install this signal package to load it, because to use the spectrogram function here called spectrogram. So that's it, guys. First video on the new YouTube channel, Digital Signal Processing Corner. I hope you enjoyed it, and give me a thumbs up and leave the comments in the section below this video. If you have any questions, I'm trying to answer them all. And yeah, see you the next time, and happy programming.